Welcome back. We're going to continue once again with our introduction to algebraic geometry. Just remember that the goal here is to define enough terms to define elliptic curve. So an elliptic curve being, we know what a projective variety is. We know when those are smooth. We know now the dimension has to do with the transcendence degree of the function field, and we know when there is at least one rational point over the field of definition of the curve. So it remains to define the genus of an elliptic curve, and that's the more complicated invariant of the curve, and that's where we're going. All right, so last time we talked about the order of vanishing at a point. We talked about uniformizers, zeros and poles. In particular, we worked out this particular example, which is important about an elliptic curve, the order of vanishing of the functions x minus ei and the function y at the points ei, 0 and at the point at infinity. And then we gave a bunch of results about curves and smoothness and when we have morphisms and so on. So what else did we see? We talked about, so if we have a map of curves that induces this injection that goes sort of the other way, if you go from, the map goes from C1 to C2, the function field of C2 injects in the function field of C1 via this map phi star. And that is a finite extension of function fields. And we saw that there are these cool relations between function fields that you have. A map gives you an injection of function fields, but if you have an injection of function fields, that also gives you a map. And if you have a subfield that is a finite subextension of a function field that contains the base field k, then that also gives you a curve and a map that induces this injection. We defined the degree of a map via this extension of function fields. And by the way, that corollary, I forget if I mentioned, an important corollary is that if you have a map of degree 1, and C1 and C2 are smooth maps, then that is an isomorphism, because you have an injection of function fields where the function field is an identity, or an injection of function fields and the index is 1, so those two function fields are isomorphic. And then it gives you, the theorem above gives you the other direction of a map. And there, because they're smooth, they're both going to be morphisms, and that gives you an isomorphism. Okay. We saw again an important example. If you take the map that takes an elliptic curve and preserves the x coordinate, this is for a particular elliptic curve, but this works for any elliptic curve. This is a map of degree 2, and we saw that because we can compute the degree of that extension. What else? And then we were talking about ramification. So when you have a map such as the one that we had before, so in the map, this map in the example, you have an elliptic curve that looks like this, and then what the map is doing is just keep the x coordinate. So these 2 points, this point maps there, these points maps here in this P1, that is the x-axis. And the problem is that some points only have one pre-image, such as that point. So this point, we're going to say that there is ramification at that point, while these ones, these 2 other points are fine. Okay, so that is the definition up above of ramification. And we saw in last class, we saw the example at p equals -1, 0, that the ramification is 2. Okay, so that is the point that I described up here. There is a ramification right there. And you can do the same thing for these points. So for example, I looked at this point up here that I'm going to call Q. This was P, and there was ramification there. At Q, so in this part of the example, I do the same thing. So you look at phi of Q. Phi of Q is just the point 0 in P1, so 0, 1 in projective coordinates. Uniformizer is given by X. Then take phi star of X, and that is going to give you in the composition, see what that is. In this case, it's just X again. Again, these sort of X's are a little bit different. This is the X coordinate in P1. This is the X coordinate in E, so you have to keep track of that. But we know also the vanishing at X. So that is something that you can work out. So this is what I'm working out in this part of the example here on the right-hand side, where because we know that the point Q is smooth, we know that this maximal ideal, the localization is generated by X and Y minus 1 because of the smoothness that has to be one-dimensional. And Y minus 1 is actually in the ideal generated by X because of this relationship. This is a unit. At that point, this doesn't vanish. Y plus 1 doesn't vanish. So Y minus 1 is in the ideal generated by X. Okay. So then the ideal, you can just generate it by X, and therefore that X has to vanish to order 1. Otherwise, it would not be that MQ mod MQ squared would not be one-dimensional as it should be because it's a smooth point. So the order of vanishing at X is 1, and that gives you that the ramification index is 1, which means it's unramified at Q, as the picture sort of shows. There's 2 points that map to this 0 point in the P1. All right, so let's move on to another point. So what happens at infinity? So at infinity, algebraically, you can just do the same way. So you take phi of O. Phi of O goes to 1, 0, which is the point at infinity at P1. And for P1, the points A, 1, the uniformizer is X minus A. So what is the uniformizer at infinity? Is going to be 1 over X. Okay, so 1 over X vanishes at infinity to order 1. And when I send it through phi star, like here, I get 1 over X on the elliptic curve. Now, what is the vanishing of X at the point at infinity? Oh, well, I didn't compute that precisely, but we did compute in the previous class the order of vanishing at infinity of X plus 1, because E1 in this case is minus 1. Okay, so you have that the order of vanishing at infinity is minus 2 in that, because we computed already that fact. Okay, here the order of vanishing at infinity being minus 2 of X plus 1, you see, so what I'm saying is that there is a pole of order 2 at X plus 1. 1 doesn't have any poles, so the pole has to be at X. So that's why the order at X and the order X plus 1 of O is both minus 2 a pole. All right. So then we have that the order of 1 over X at O is 2, and that gives me through the formula, it gives me the ramification, and there is ramification at O. Okay, so there is ramification at O, and there is ramification at P, which was minus 1, 0. It turns out there is 2 other points that are ramified. But before I say that, I mentioned last time, like you can also see this at infinity. It's hard to see what is happening at infinity to tell whether there is ramification. So you can change your chart. If we change the chart to the y equals 1 chart, then I get a different form for my elliptic curve. The elliptic curve looks like this sort of a squiggly snake. And the map phi now is a little bit different. It's not just pick the x coordinate, it's X over Z. And then you can see that the points, let me see what color should I do here. These points like before they actually go to 0, so there's 2 preimages of 0, so that is not ramified, but this point is the only possible point that goes to infinity. Only when z equals 0, I might actually go to infinity, and that's what happens. At that point, at 0, 0, it does go to infinity, and there's only one point above infinity there, so there's ramification at infinity. All right, but what I was saying is that, so a question for you, for the audience here. So if you look at this graph, so this, we've seen that there is ramification at infinity. Okay, so O is ramified. Okay, so infinity here in P1, O goes there. So, and then P goes to P here. Where are the other ramification points? There are 2 more. Where do you think there are more ramification points? It doesn't look like there is any more, so why would I think there is more? It turns out that you have to look at the ramification, you actually have to look over the algebraic closure. And over the algebraic closure, the polynomial x cubed plus 1 factors, and there's 3 solutions. So this is actually y squared equals, yes, x plus 1, but then also x plus a row and x plus some row squared or something. So it's third roots of minus 1 of yeah, third roots of minus 1. Okay, so like that. So those points, although we can't see them in the real in a real chart, those points also will have ramification. So these correspond to the PIs, the EIs, comma 0. All of those are ramified in this map. Okay, and we were just seeing the P was P1, which was the point minus 1, comma 0. That was when was ramified. Okay, so there is more ramification. So there's actually 4 ramified points: P1, P2, P3, and O. Okay, so let's keep going. Let me write here a proposition with some.
All right, Alvaro, could we
Yeah.
this very quickly? So I'm sorry if I missed this, but so the ramification is defined over the algebraic closure of the set under consideration, not over, say, like if we were to talk about the points that ramify on that elliptic curve, we would care about the algebraic closure of Q, not over Q itself.
I mean, the ramification is the definition of ramification is just for a point, right? So you take one point, a map, and I tell you if it's ramified or not. But what it turns out is that we're going to need to know the ramification at all the points. We are going to need to know all the ramified points, including points in the algebraic closure.
Okay.
So in a moment we'll see, or I hope today or next time, we'll see, for example, the Riemann-Hurwitz formula, and that involves ramification, but then you have to find all the points that are above in a fiber and find the ramification on all of those points. Okay, so you do need to know all the points that may be ramified, including over the algebraic closure. Okay. So here's a
thank you.
Yep, here's a proposition. So with phi a non-constant map of smooth curves, and let's take P to be in C1. Then first, the sum of ramification indices at P over points of a point Q. So let's pick a point Q in C2. So if you add up all the ramification indices, what do you get? You get the degree of the map. Okay. If you remember again the map we had before, so something like this that we're sending points to their x coordinate, then you see, remember that the degree of this map was 2, and the pre-images of these points, so if this is Q, this is P1, and this is P2, the ramification here was 1, and the ramification here is 1, and 1 plus 1 is 2. That's what this theorem is saying. And at this point, P here, there is only 1 point above it, and the ramification in here is 2. So 2 plus nothing else equals 2. So that's what this part of the theorem says, which makes sense. B, for all but finitely many points in C2, excuse me, the number of preimages, the number of points in the preimage of Q is the degree of phi. Actually, is the separable degree of phi. So remember that if we are working over fields and characteristic P, we might have separability issues in the extensions. So this is the separable degree of the extension of function fields. Okay. And so you see that in this on this elliptic curve, what happens is that there's actually 4 points where this fails to be true in our example of the projection. The points P1, P2, P3, and the point O. All the other ones have exactly 2 preimages. Okay. By the way, this was a question after I turned the video off. Ben asked this question: if you have a map, can there be infinitely many ramified points? And this part of this theorem tells you that no, there's only finitely many places where there might be ramification. You see that if the number of points is the degree of the function, then because I'm adding on this part, I'm adding things that are at least 1. If there are already degree of phi preimages, in characteristic 0, so the degree of phi and the separable degree are the same. If there are degree of phi preimages, then all the ramification has to be 1 at those points, so they're all unramified at those points. Okay, so this tells you that there is ramification only at finitely many points, which is nice. And by the way, also, if you look at the geometry or the calculus of it, you can see that the ramification is going to happen at sort of like critical points where something is happening with the derivatives. So it has to be a condition which is some finite condition of some derivative vanishes or something that is making this happen, right? So you can see where this comes from, this condition comes from for the ramification to be only a finitely many points. And C, if you have another non-constant map, then the ramification index of the composition is the product of the ramification indices. Okay, this is analogous to the fact that in number fields, the ramification indices are multiplicative in towers. When you have a number field and an extension of number fields, and you're looking at how a prime ideal ramifies all the way up, then the ramification in the tower, the ramification indices are multiplicative in the tower. This is the same concept. Okay, then corollary to this. is that phi is unramified everywhere, so unramified, if and only if the number of points for all Q in C2. Okay, so you have to have that you always have the same number of preimages, then it's an unramified map. Okay, so now that we have that, we are ready to talk about divisors. Okay, so maybe this is a good point to stop this recording, and then I'll do a recording for divisors entirely.